program called readelf will take an elf file and show you a lot of this basic information. So let's try that out ourselves. Here I have a file that I've called demo. It defines get A and get B and set A and set B, which works on arrays. The A array is declared here, the B array is not declared here. If we compile that, so let's see, I'm going to use C and demo.c. So now I have demo.o, and I can use readelf on demo.o, and since demo.o is a file, an elf file, then it'll print all sorts of information, and there's a bunch that scrolled off here. So let's send this to a file D and look at it in the editor. Start at the beginning. So at the beginning there's some general elf information here. Notice it knows that this is an elf64 file because we're on a 64-bit platform, and that it uses 2 complement numbers, and it's little endian, as we would expect. It also says rel for relocatable file, so that's another way of saying object file, and it's for x86-64. And if we go down to the next bit, then we have the section headers listing. So this tells us all the sections in our file. Demo.o has a text section, it has a data section, and the string table, and symbol table, and so on. It says there are no program groups, or actually it says there are no program headers in this file. That's because it's an object file. And there's some more information about various of the sections that readelf knows about, and we'll come to that later. If I take demo.c and link it together with main.c, so main just calls get A and also supplies the variable B, then we can put these together in an application a.out by looping main.c with demo.o. And let's use readelf on a.out to get to. So this time you see it says it's an executable file. We have a similar set of sections. We do have an interp section because this is going to be dynamically linked to the C library. Instead of a symbol table and strings, we have a dynamic linking symbol table and dynamic strings, but it turns out to be about the same thing. There's some other stuff in here. There's a text section, there's a read-only data section, and there's a BSS section, and so on. We also have a regular string table and symbol table. That's the sort of minimal debugging information that's in this file. And since it's an executable, it has program headers. In both the section headers and program headers, let's look back at section headers for a minute, you see that there is an address and an offset for all of these pieces. So offset corresponds to where do you find it in the file, and address corresponds to where is it going to be mapped into memory when this file is actually run. So for example, the text, let's look at the text segment. We would need to go hex 40 bytes into the file to find the machine code in this file, but various things arrange for that to be mapped at address hex 400400. Meanwhile, the same sort of mapping is in the program headers area. So we see that some code being loaded is from hex 4 with 5 zeros, and the length on that, the size, is 774 bytes, so that includes the range where we saw the text. So that means text is in this region. This particular segment covers the text section. You can see something else that makes sense here. This region, this segment is marked as read-only, but also executable. Whereas this other segment, which is at 6, hex 600 E10, going for a while, that's a section that's not executable, but it's readable and writable. And so I bet that's where the data segment maps to. Let's see if the data segment is consistent with that. Let's see, yes, the data segment is mapped to 601028, and that corresponds to a region that's covered here in this section as well, segment as well. So in an executable file, you see both segments and sections, and you see how there's sort of different attributes attached to each of those views, but they cover the same bytes of the file and the same addresses in memory.